Introducing SIM4BC, your cybersecurity ally. SIM4BC is an innovative cyber incident simulation system designed to bolster defense capabilities against cyber-physical incidents. Enhancing cybersecurity with SIM4BC. In a world where real-world attacks can disrupt critical services, impacting organizations globally, safeguarding modern digital interconnected infrastructures becomes paramount. But how do we protect critical infrastructures effectively? SIM4BC offers a proactive approach to threat mitigation for system security engineers in charge of conducting system security engineering activities like the implementation, maintenance, and assessment of the security measures of the system. Join us as we dive into the future of cybersecurity simulation. As cybercriminals become more sophisticated, understanding these threats is crucial for effective defense. The EU Directive on Resilience of Critical Entities highlights the need for these entities to enhance their capabilities in order to prevent, protect against, respond to, and recover from incidents that may disrupt essential services. Given the dynamic nature of cyber threats, there is an increasing need for proactive security measures. Organizations must adopt robust defense capabilities to safeguard critical services and infrastructure. Staying informed and vigilant is key to maintaining resilience. According to the last ENISA Threat Landscape Report, one of the most alarming findings is the significant increase in ransomware attacks. Organizations of all sizes are grappling with the impact of these malicious campaigns. Ransomware not only jeopardizes data integrity, but also disrupts business continuity and financial stability. Attacks targeting availability, such as distributed denial of service, are on the rise as well. These attacks have become more complex and sophisticated, posing challenges for organizations' network resilience. Ensuring robust defenses against this type of attacks is essential. Conducting attacks and evaluating incidents within a real or emulated environment can be challenging and costly for organizations. On the one hand, triggering incidents in a real system, especially one on which business continuity depends, is not a realistic option. Essential services cannot be interrupted for security assessments. On the other hand, creating a representative replica of the system poses its own challenges. The system's complexity, with numerous nodes and varying characteristics, makes replication a daunting task. Adjusting the replica's configuration based on the type of attack or incident adds yet another layer of complexity. When no actual system is available for evaluation, the digital twin becomes an excellent alternative. Unlike tangible systems, the simulation of attacks in this scenario relies on simulation models. These models simulate specific system attributes relevant to the incident scenario and evaluation goals. In recent years, a groundbreaking technological approach has taken center stage: the use of generative adversarial networks. GAN-based models exhibit remarkable potential in replicating diverse types of data. To enhance incident depiction within the system, cybersecurity experts are including a wider range of incident indicators beyond the commonly used network traffic data. In summary, by embracing innovative approaches, we can better defend against cyber threats and ensure the resilience of essential services. How can system security engineers evaluate and enhance defenses without disrupting ongoing business operations? Check our innovative system, a solution that enables simulation of cyber-physical attacks and incidents without jeopardizing essential services using virtual simulations. Our approach is multi-layered, combining threat modeling with synthetic incident data generation. We employ a graph-based approach to model threats within the system. This expert system predicts the effect of incidents, allowing us to identify the affected assets. Our AI-based system accurately replicates multiple layers of the target system. It simulates data trends from real incidents, providing a comprehensive view for security implementation and evaluation. But how does it work? Our journey begins with the analysis of a real-world incident and the collection of multi-layered datasets and incident reports that will be meticulously compiled, encompassing everything from network traffic to system behavior. Our system takes this vast amount of data and transforms it into a dynamic simulation, allowing users to immerse themselves in a virtual reconstruction of the incident. This solution allows you to model incidents using attack graphs, providing a visually appealing representation of attack scenarios and pathways. By understanding the attack surface within your system, you can proactively strengthen your defenses and safeguard your organization from malicious attacks. With our system security engineers can easily configure a detailed data generation plan, allowing for the simulation of various types of data based on their relevance and significance to your specific scenario. Our simulation system creates synthetic incident data that closely mimics real-world attack patterns, providing invaluable insights into the resilience of your systems and the effectiveness of your security measures, including intrusion detection systems. Welcome to the demonstration of SIM4BC component. This demonstration is based on the use case involving the infrastructure of electric vehicle charging stations using the OCPP protocol. The incident scenario to be simulated is a denial-of-service attack at the application layer that could happen if the infrastructure is compromised. Let's explore how it works. The system security engineer should start with the definition of the system architecture, that is, modeling the system that we want to protect from the attacks. The resulting system model follows a meta-model specified within DYNABIC that covers attributes related to cybersecurity in the nodes. The incident modeler subcomponent in SIM4BC plays a fundamental role. It requires as input the system architecture. This input can be specified by the security engineer or retrieved from another system component, such MADT4BC component that models the system in a graph format as well. Prepared with this system model, SIM4BC models the incident using rule-based expert system and generates an attack graph. This graph visually represents potential attack scenarios given the configuration of the nodes in the model and their pathways within the system. The attack graph is instrumental. It helps us understand the attack surface within the system. It depicts the incident's footprint across various nodes. Depending on whether the security control is able to block the attack and is enabled in the system model, the resulting attack graph will vary. Attack explanation. Our system utilizes the latest in large language model engines to provide users with detailed explanations about the attack graph being modeled. Moreover, the explanation not only explains the effects of the attack on the system, but also provides some recommendations customized for the system. Next step is the generation of the synthetic incident data. The system security engineer can configure the data generation plan. They select the type of data to be simulated based on its relevance and significance for the specific scenario and system under study. SIM4BC accurately replicates multiple layers of the target system. It simulates data trends from real incidents, providing a comprehensive view for security implementation and evaluation. In this example, SIM4BC generates data replicating network and application layers. For the network layer, it generates both network flow type data that includes 83 different attributes with 80% accuracy and OCPP-related application layer network flow type data that includes 56 attributes with 86% accuracy. Regarding application layer OCPP-related logs, 13 attributes have been generated with 90% accuracy. The simulated data can be utilized in two ways, either as a downloadable dataset for training purposes or as simulated real-time data streamed directly into the system. The system's security controls are then evaluated to determine their effectiveness in accurately detecting security incidents. Furthermore, the detected security events are shared with the broader cybersecurity ecosystem, enabling them to process the simulated incident data and respond appropriately. Thank you very much for your attention.